Hello and welcome back to AB 474, Indoor Environmental Control. We are in chapter 6, which is solar radiation, and we are in the fourth section of the series of lecture videos covering the content of this chapter. The first section was on introduction, and the second section looked at the relationship between the Earth and the Sun and how we measure time. The third section, which we just completed, was looking at solar angles, and now we're going to take that and extend it to the unknown that we had when we started this chapter, which is how much energy or how much solar radiation is coming onto a surface. If you recall in our previous problems when we were looking at the chapter on heat transfer, we made an assumption, or we were always given a value for the solar irradiation incident onto a surface. So the value of the radiation that came onto that surface from the sun. So now we're going to put the pieces of this chapter so far together and expand just a little bit further in order to calculate that value for any given day, any given time for our specific scenario. So let's go ahead and get started with that. The first thing we're going to look at is called the mean solar constant. So capital G sub SC is the mean solar constant. Oops. And this value is defined as the rate of irradiation onto a surface directly facing or normal to the sun's rays. And this value, or the value we're given in this constant is taken beyond the Earth's atmosphere, so without any interference from the atmosphere. So think a solar panel out in space. Taken just beyond the atmosphere at the mean Earth-Sun distance. Alright, so yeah, think about this as a constant that is just outside the Earth's atmosphere, so think like solar panel orbiting the Earth kind of thing. And when that solar panel is directly facing the sun's rays, so it's the most direct sun's rays hitting it, then that's what this value is representing. So 433.4 BTU per hour foot squared, or 1367 watts per meter squared. The estimate on the variation in this is about 3.5%. Due to the variation in the Earth-Sun distance. Due to variation in. However, I'm sure you've already recognized the problem with this. We generally don't use this value because it doesn't take into account. Let's see, we generally don't use. So it doesn't take into account the effects of atmospheric absorption, and as we just mentioned, the variability of this value depending on the distance between the Earth and the Sun. But you can expect that the value that's coming onto the Earth's surface is going to be something less than this, because certainly the atmosphere is going to absorb some of the energy and it will never reach the surface of the Earth. So we do have a process by which we estimate what's coming onto the Earth's surface. So we have some more variables that we're going to take a look at. So capital G sub ND, we can call this normal. You might see it called normal, or direct radiation, or direct normal radiation, or beam irradiation. So there's a number of different values, or different variable names we might hear that are all referring to the same thing. And this is referring to the part of solar radiation that comes through the atmosphere from the sun that is neither scattered nor absorbed and reaches the Earth's surface, and thus the surface that we're interested in. If you want to think of it in practical terms, this is the radiation that casts a shadow. So the radiation itself isn't casting the shadow, but if you want to think of it in terms of, some of the radiation that's coming in gets scattered, but still reaches the Earth's surface. Some of it gets absorbed and may then be re-emitted, or absorbed by the atmosphere and re-emitted, or absorbed by some other surface that's not the surface we're looking at and re-emitted. But there's some portion that comes straight through and reaches the surface. And if we were talking light, scattered light, absorbed light, those sort of things aren't the ones that cast a shadow. The light that reaches the surface is what casts the shadow. So if you want to think of it in those terms, it's kind of the unadulterated radiation that reaches our surface. The next portion of our radiation we want to look at is abbreviated in our text as capital G little d, and it's might be called global. Might also be called diffuse radiation, so global radiation or diffuse radiation. And this is going to be the part of solar radiation that was scattered but reaches the Earth's surface. Plus that which is absorbed and re-emitted and reaches the Earth's surface. And then the next type of radiation that we might encounter, is the reflected radiation. And it is abbreviated with a capital G as well, and a subscript capital R. And so this is the part that hits a different surface nearby and then is deflected onto the surface we're interested in. That's a different surface. And then if we combine all the components, we are going to get what is referred to as the total solar irradiation onto a surface. And this capital G sub small t is specifically the total solar irradiation onto a surface if it were normal to the sun's rays. And this is where our angles from the last section will need to come into play to correct for a surface that is not normal to the sun's rays. All right, and our total radiation, total irradiation, is the sum of the direct normal portion, the diffuse portion, and the reflected portion. So if we want to visualize for a moment or two why it is that we need these different portions, so let's spend just a minute talking about the Earth's atmosphere. So the sun's rays that are coming onto the Earth's surface are affected by stuff in the atmosphere, which we've already kind of talked about. As well as how much, so the length that it takes to pass through all of the atmosphere. And so let's visualize that for a minute to convince ourselves that that is an important consideration. So we're going to test my art skills. I decided in the last section to not test my art skills and let you refer to the figure in your textbook, but in this case we'll give it a try, and if nothing else we'll get a little comedic break. Alright, so if we want to think about kind of the closest pass, so the sun is the highest in the sky at midday, and so this is our sun, and this is the path of the sun's rays. In order to get through the atmosphere, they have to pass through a distance of this. Now, both earlier and later in the day, so let's say right about here. Hopefully I put that in the right place. It might be off by just a little bit. Let's kind of shuffle it a little bit. At sunrise or sunset, our sun's rays are going to be coming to the Earth, and they're going to have to pass, there we go, a whole lot further to get to the Earth's surface. There we go. And then likewise. Or the other sort of angle of approach can vary So this kind of gives us different points on the Earth's surface. What if we're looking at a single point on the Earth's surface, and you think of the sun being oriented at different locations throughout the day? So it's a little bit off. I should have written my word "or" a little further away. But so if the there we go. If the sun is in that position, it's the shortest, and let's just draw it this way. It would be the longest path if the sun were in this position. Okay, so if we represent with a little m, and I apologize for the duplication of variable names, I'm going with your book. If we represent using a little m, the air mass ratio, we can again help to use it to explain this need to account for where we are and when. And so the mass of atmosphere in the actual, sorry, I'm out of room, so I'm going to have to put 2 lines on here. Sun-Earth path divided by the mass of atmosphere if the sun were directly overhead at sea level. So think of this here as this is directly overhead. So this is the maximum that's ever going to reach the Earth's surface. And then all along the path between here and here, you have various amounts of atmosphere interfering. So this air mass ratio is just the ratio of how much is actually there, how much is actually being interfered with versus how much potentially could be in the best case scenario. So now what we're ready to do is figure out how do we calculate those irradiation values, so the direct, normal, the diffuse, and the reflected. How do we actually put a value to those? ASHRAE has a model that we're going to apply in this class called their clear sky model, and essentially it applies a correction for clearness, so for clearness of the sky. And it is used to calculate, to estimate, to predict solar irradiation, and sometimes in the texts and the references will be called the intensity. So solar irradiation or solar intensity. At the surface of the Earth on a clear day. Right, and the equation in this model is not terribly complicated. The direct normal irradiation is a constant, A. Well, it's a variable A, but we get the value out of a table, so we don't have to do a calculation for it. Divided by B, which is also a value that we take from a table, over sine beta, which we've seen before in terms of our solar angles, times this clearness number. So let's look at what each one of these components of this equation are made of. So the A is called the apparent solar irradiation if our little m up above is 0. And we're going to look at table 7.2 to get this value. This is kind of our starting estimate, kind of like we had the value if we were in outer space. This is kind of the best estimate value to start with. Okay. B is going to be called our atmospheric extinction coefficient. C sub n is our clearness number, and can be taken off. It's represented as a percentage, and we can take it from figure 7.7. And in that figure, S stands for summer, W stands for winter. That, while it seems intuitive now that I've told you, isn't entirely clear from the figure itself. And then the value that we're solving for is the direct normal radiation, or normal direct irradiation for a horizontal surface. So that's the important part I want to reiterate here. So next question. What if our surface is tilted? Okay, so if our surface is tilted, then we need to take the normal direct irradiation calculation that we just did above, that value, and we need to do a correction. And that's just going to be called direct radiation as opposed to normal direct. And it is the normal direct value multiplied by the cosine of our angle of incidence. If you recall, we got that one toward the end of our angles in the last section. If our angle of incidence is less than 0, then we have no direct irradiation on the surface. We can still have irradiation on the surface, but it can't come in the direct sense. It can come from reflection mostly. If we want to get the value for diffuse, first we start with the value for a horizontal surface, and then we'll do a correction for the tilt again. So the diffuse is a constant multiplied by the normal direct, and that constant can be attained in table 7.2. And it is can be described as the ratio of diffuse radiation on a horizontal surface to the direct normal radiation. And while it is assumed to be a constant for our calculation purposes, in reality it is a variable. Okay, and then if we want our diffuse for a tilted surface or a non-horizontal surface, then we need to make a correction. So and we're going to make that correction using a configuration factor. If you recall, when we looked at radiation in the heat transfer section, we've heard of configuration factors before. And as with many cases, there's a number of different names. So it could be called the configuration factor, it could be called the angle factor, it could be called the shape factor, all referring to the same thing. To help us better understand the fraction of diffuse radiation leaving one surface and falling onto another surface. So we'll look at a couple of special cases. So vertical is probably the most common special case we run into with buildings and structures. So for vertical surfaces, the diffuse value is C times the direct normal times the ratio of diffuse on the vertical surface to diffuse on the horizontal surface. But there is an equation, because it seems like we just went in a circle right there. Equation 721 in your book gives the predictive relationship for solving for this ratio. 0.437 plus 0.313. So this is the equation for cosine theta greater than negative 0.2. And as far as I know, these equations are essentially curves fit to a data and aren't derived from anything. But I could be wrong about that. This is a little outside of my strongest area. So if our cosine theta is greater than negative 0.2, then you use this more complicated equation, or there's a much simpler, we just use a constant, sorry for the scribbles, 0.45 otherwise. Alright, so we're going to take just a quick pause to talk about a little bit of vocabulary that shows up in ASHRAE. And there's an assumption that is important to acknowledge here. So anisotropic. The ASHRAE model assumes that we are anisotropic for vertical surfaces. And what that means is the brightness varies. But that we are isotropic for horizontal surfaces. And what isotropic means is the brightness is uniform. The last portion that we need to put a value to is our reflected radiation. And it's going to be reflected from the ground and surroundings. There's a couple of scenarios we could think of that you might have some significant impacts of reflected radiation. So if there's an asphalt or concrete parking lot that runs up next to your building all the way up to the edge, and potentially the mix in it has a lot of reflective materials, you might have a significant reflective portion onto your building. Or if you have a body of water that is up next to, very close next to your building, that could be reflecting onto your building. All right. So the reflected radiation can be calculated as so this is the irradiation that falls onto the surface that your reflected portion is coming from. So this is the radiation onto the surface in front of the wall or the vertical surface that you're interested in. And this is the reflectance of the ground or the horizontal surface, if it's not the ground. So if it's water or a pavement or something like that. And then we've seen capital F before as a shape factor. So this shape factor can be calculated as 1 minus cosine of the tilt angle over 2. And reflectances for, so some important ones that you're going to want to know. Fresh snow, so fresh snow, meaning it's still very sparkly and shiny. 0.8, so very high reflectance. Snow that's been there for a while but has lost some of its sparkle, 0.5. Grass and concrete, 0.2. And you can look up others as needed. For example, I don't have the one for water for you. I'm sure there's some qualifications in there for what type of water and how reflective it is. All right, so at this point, we can now calculate the total irradiation onto a surface. And so let's go ahead, let's just summarize what we can do at this point. We can now get the total irradiation onto a non-vertical surface. And so essentially we can substitute in each of the individual relationships that we've looked at. With this little th, I'm not sure I told you this is total horizontal. Okay. Let's see, if we want to simplify this total horizontal piece, so if you recall, for a horizontal surface, the cosine of this angle of incidence is equal to the sine of our beta. cosine theta equals sine beta. So let's refresh ourselves and go back and look at it if you don't remember that. And so if we want to simplify this equation, our total irradiation onto the surface I left something out earlier. Let's see. Okay, so this is our full equation. We saw earlier we have two different shape factors, and earlier I forgot to define this shape factor, so I'm going to take the opportunity to go ahead and do that now and refresh ourselves on this shape factor. Where the alpha in both of these is the tilt angle. Okay, so let's do a few more simplifications here. So if sine beta is less than 0, then the total irradiation onto the surface is 0. For a horizontal surface, our shape factor for reflected is 0. So our reflected portion is 0, in which case, so if we have a horizontal surface, our irradiation total onto that surface is just the sum of the direct and the diffuse times our direct normal. All right, and second special case, if we have a vertical surface, scoot it up here so you can see. Sorry if I cut that off earlier. I'll leave it up here. Let's go to there. Okay. I almost didn't leave enough space here, but this is the direct normal times all of these, the sum of the three coefficients for direct, diffuse, and reflected. Okay, and I think with that, that's going to wrap up this section on calculating solar irradiation. So let's kind of take a short look back at where we were. So this kind of wraps up the summary of all of this piece, where our total radiation onto a surface is represented by this equation, which is the portions of direct, diffuse, and reflected onto a surface, and then we have two special cases for a horizontal and vertical surface, but you can figure it out regardless of the orientation of your surface. The last thing we're going to do in the next section is to tie it all together to talk about the heat gain to our structure based on that contributed from the solar radiation. So we're gonna tie it together and wrap up in the next section. So come back soon.